Hello everyone, and welcome to this cosmic journey. Tonight, we're embarking on an exploration unlike any other. We're not just talking about the universe, we're going to feel it, experience it, in its own majestic rhythm. We're diving into a slow documentary, not with a camera crew, but with our minds, to witness the grand, patient unfolding of creation itself, the universe, and the birth of something truly monstrous, yet utterly essential, a supermassive black hole. Think of it. The cosmos doesn't rush. It breathes. It evolves over scales of time and space that frankly defy our everyday comprehension. We're used to minutes, hours, years. The universe? It counts in billions of years. So, tonight, we slow down. We dim the lights in our minds, and we open ourselves to the greatest story ever told, played out in excruciating, beautiful slow motion. Imagine standing on a silent, desolate shore. Instead of waves crashing, you hear the distant echoes of the Big Bang itself, not a bang, really, but an expansion, a cooling, a stretching of space and time. This is where our story begins. Just fractions of a second after that primordial inflation, the universe was a searing, opaque plasma, too hot for light to travel freely. It was a cosmic soup of fundamental particles, swirling, colliding, unable to settle. For hundreds of thousands of years, this blinding fog persisted. The universe was dark, in a way we can barely conceive. No stars, no galaxies, just a featureless, expanding void, still simmering from its birth. This era? We call it the Cosmic Dark Ages. A truly fitting name. But even in this darkness, the seeds of complexity were being sown. Gravity, that persistent, invisible sculptor, was already at work. It was pulling, ever so gently, on tiny fluctuations in the density of matter. These weren't dramatic events, not yet. These were subtle tugs, imperceptible shifts, gradually gathering wisps of hydrogen and helium gas, along with the mysterious, unseen scaffolding of dark matter. Think of it like a whisper in the dark, slowly, patiently, drawing molecules together over billions of cubic light-years. It was the universe holding its breath, waiting for the first spark. Then, after about 400 million years, a blink in cosmic time, but an eternity to us, something incredible happened. Enough gas and dark matter had accumulated in these nascent gravitational wells. The pressure and temperature at their cores reached a critical point. Fusion ignited. And with that, the universe was born anew. The first stars blinked into existence. These weren't just any stars, though. These were truly magnificent, colossal objects, utterly unlike our Sun. We call them population 3 stars. Imagine stars that are hundreds, even thousands of times more massive than our Sun. Primitive. Pure. Made almost entirely of hydrogen and helium, forged directly from the raw ingredients of the Big Bang. No heavier elements to muddy their composition, to cool their cores, or to slow their birth. They burned with an incandescent ferocity, hotter and brighter than anything we see today. Their lives were brilliant, but tragically short, perhaps only a few million years, compared to our Sun's 10 billion. They were cosmic fireworks, illuminating the dark ages, pouring out ultraviolet radiation that ripped through the remaining neutral hydrogen, reionizing the universe and making it transparent to light. These first stars were the pioneers. They were the lighthouses guiding the formation of the first tiny galaxies, often called protogalaxies. Picture these as fragile islands of light in the vast, still dark ocean of space. They were small, irregular, chaotic collections of these massive, short-lived stars, bound together by gravity and nestled within enormous halos of dark matter. These were the very first galactic nurseries, the building blocks of the grand spirals and elliptical galaxies we marvel at today. And as these majestic, pristine stars roared through their lives, they were also setting the stage for something far more profound, and far more terrifying. You see, when a star that massive dies, it doesn't just fade away. It collapses. Catastrophically. A supernova explosion from a population 3 star would have been an event of unimaginable power, scattering newly forged heavy elements, carbon, oxygen, iron, out into the nascent cosmos. But the very most massive of these first stars, those exceeding perhaps 200 times the mass of our Sun, met an even more dramatic end. They might not have exploded in the conventional sense. Instead, they could have collapsed directly, completely, into a black hole. Not just any black hole, but a seed black hole. And this, my friends, is where our slow documentary really begins to focus. This is where the universe starts to hint at its hidden, powerful heart. These stellar remnants, these gravitational anomalies, were the very first black holes. Tiny, perhaps, by supermassive standards, but the initial building blocks of the monsters we seek to understand. Each one, a tiny tear in the fabric of spacetime, where gravity has won an absolute victory. But what is a black hole, truly? Forget the science fiction clichés for a moment. At its heart, a black hole is simply a region of spacetime where gravity is so incredibly strong that nothing, not even light itself, can escape its grasp. It's not a cosmic vacuum cleaner, sucking up everything in sight. It's a cosmic point of no return. Cross the event horizon, that invisible boundary, and you're gone. Forever. The mass of a black hole is concentrated into an infinitesimally small point called a singularity. It's like taking an entire star and squeezing it down to something smaller than an atom. The density is infinite, the physics, mind-bending. Now, imagine something like that, but not just the mass of a single star. Imagine it having the mass of millions of suns. Or even billions. That, ladies and gentlemen, is a supermassive black hole. Sagittarius A*, the black hole at the center of our very own Milky Way galaxy, weighs in at about 4 million solar masses. The largest ever discovered? Over 66 billion times the mass of our Sun. Absolutely staggering. The central mystery of our story, the great cosmic puzzle, is this: how did these colossal gravitational behemoths form, especially so early in the universe's history? We observe supermassive black holes just a few 100 million years after the Big Bang, far too quickly, it seems, for them to have grown simply by devouring a star at a time, or by slowly merging with other stellar black holes. The universe hadn't even had time to build many stars, let alone for them to live out their lives and collapse. This is the crucial plot point, the cosmic dilemma that astrophysicists grapple with. This is where the slow documentary becomes a detective story. We have theories, hypotheses, and computer simulations attempting to unravel this deep enigma. Let's explore the most compelling ideas. One leading theory speaks of direct collapse black holes, DCBHs. Picture this: instead of forming stars, some immense primordial gas clouds, perhaps 100,000 to 1,000,000 times the mass of our Sun, simply collapsed directly. No intermediate stellar phase. No explosive fireworks. Just a rapid, catastrophic implosion. What would be the conditions for such a thing? Well, you need very specific, almost Goldilocks conditions. You need pristine, unpolluted gas, untouched by the heavier elements forged in those first supernovae. You also need to prevent this gas from cooling too quickly and fragmenting into smaller, star-forming clumps. This might happen in environments where there's a strong UV radiation background from nearby starburst galaxies, which keeps the gas hot and prevents it from forming stars. Or perhaps, when two protogalaxies merge, the chaotic collisions of gas clouds create a massive, unstable blob of gas that can't find its footing and just collapses under its own immense gravity. If this happened, you wouldn't get a few stellar mass black holes. You'd get a single, massive seed black hole, potentially tens of thousands to hundreds of thousands of solar masses, right out of the gate. This would give it a massive head start, allowing it to grow to billions of solar masses very quickly. Another theory, though perhaps better suited for later stage growth, involves the runaway merger scenario. Imagine those first small black holes, the remnants of the population 3 stars. In the chaotic, dense centers of early protogalaxies, these black holes wouldn't be sitting still. They'd be spiraling inward, drawn by the combined gravity of the core. As they get closer, they might collide, merge, and form larger black holes. This process repeats, with the bigger black holes sinking deeper, merging again, and growing exponentially. It's like a cosmic game of Pac-Man, but with black holes instead of dots. The challenge here is the timescale. While mergers certainly happen, the rate might be too slow to explain the most ancient supermassive black holes we observe. Then there's the concept of hyper-Eddington accretion. This gets a bit technical, but it's fascinating. Normally, as a black hole feeds on gas, the gas gets incredibly hot and emits intense radiation. This radiation pushes back against the incoming gas, creating a limit on how fast a black hole can accrete matter. It's called the Eddington limit. But in the early universe, with its abundance of gas, and perhaps under certain conditions like highly irregular accretion flows, a black hole might have been able to temporarily exceed this limit. It would be like a cosmic vacuum cleaner with a broken thermostat, sucking in gas at an unprecedented, ravenous rate, growing incredibly fast in a short period. So, the birth of a supermassive black hole isn't one simple story. It's likely a combination of these mechanisms, playing out under the chaotic, energetic conditions of the early universe. It's a tale of perfect storms, immense gas clouds, violent mergers, rapid accretion, all converging in specific locations to create these gravitational titans. And what's the evidence for all this cosmic drama? Look to the quasars. These are the beacons, the most luminous objects in the universe. A quasar isn't a black hole itself, it's the incredibly bright disk of superheated gas swirling around a supermassive black hole, right before it plunges past the event horizon. This accretion disk glows with the power of thousands of galaxies. It's like a cosmic lighthouse, shining across billions of light-years, allowing us to see these active supermassive black holes as they were billions of years ago, in their youthful, voracious prime. When we look at the farthest quasars, we are essentially looking back in time to the very nurseries where these giants were just being born and feeding like mad. These black holes aren't just passive gravitational sinks either. They are architects of galaxies. When they're actively feeding, they generate powerful jets of plasma and radiation that can stream out for millions of light-years. These quasar winds or AGN feedback, active galactic nucleus feedback, can profoundly influence their host galaxies. They can heat up gas, preventing it from collapsing and forming new stars, effectively shutting down star formation. Or, in other scenarios, these outflows can compress gas, triggering bursts of star formation. They are cosmic regulators, shaping the evolution of the galaxies they inhabit, often found at the very heart of these systems. The black hole and its galaxy grow and evolve together, a symbiotic, if sometimes violent, relationship. Our own Milky Way has Sagittarius A* at its core. Today, it's a relatively quiet giant. It mostly munches on stray gas clouds and occasional stars, emitting only faint radio waves. But it wasn't always so docile. Evidence suggests that in the past, perhaps just a few million years ago, it was much more active, perhaps even a miniature quasar, influencing the structure of our galaxy. The two massive Fermi bubbles of high-energy gas extending above and below the galactic plane are remnants of this past activity. So, here we are, at the end of our slow documentary. We've journeyed from the utter simplicity of the Big Bang to the complex, gravitational dance that built the first stars, then the first galaxies, and ultimately, the enigmatic, monstrous, yet beautiful supermassive black holes. We've seen how these cosmic behemoths, born under extreme conditions, quickly rose to power and began to shape the very fabric of the universe. The story of the universe is not a series of quick cuts. It's a long, sweeping epic, filled with moments of intense drama and stretches of profound, patient evolution. The birth of a supermassive black hole is one of its grandest, most mysterious chapters. It reminds us of the incredible power of gravity, the intricate dance of matter and energy, and the fact that even in the vast, cold emptiness of space, there is constant change, constant creation, and constant revelation. The universe continues to unfold, slowly, patiently, revealing its secrets one by one. And by slowing down, by truly contemplating these epic scales, we gain a deeper appreciation for our own fleeting existence within this magnificent, ongoing cosmic story. Thank you for joining me on this journey. Keep looking up, and keep wondering. The universe is waiting.